All right, in this section, we're going to look at Lhopitals rule and indeterminate forms. Now, there are several different indeterminate forms we're going to look at, but the ones we're going to look at in this first part are the 0 over 0 and infinity over infinity forms. And most of the other ones that we look at, we're going to evaluate them by turning them into these. Not all of them, but most of them will do that way. So anyway, they're called indeterminate because they're undefined, and also because limits that have these forms can take on any value from minus infinity to infinity. Before we look at Lhopitals rule, let's look at this down here. This limit, if you just plug the 3 in, up top you'd get 9 plus 3 minus 12, which is 0. And on bottom you'd get 9 plus 6 minus 15, which is 0. So this is a 0 over 0 type limit. And it's indeterminate, and we've already seen how to deal with some of these. This one we could factor and cancel and probably get something nice out of it. This one down here, we've seen how to deal with these before too. When x goes to infinity, the top of this thing is going to grow large, and the bottom is going to grow large as well. And we've seen how to deal with this, but we're going to see a new way to do it now. What Lhopitals rule says is if you've got two functions that are differentiable let's just look down here to begin with, because this is the most important part. If you have an indeterminate limit of the type infinity over infinity or 0 over 0, what you can do to evaluate that limit is take the limit of the derivative of the top over the derivative of the bottom. Let me show you. This first example, we've got this. We looked at it a second ago and saw that this is a 0 over 0 type limit. So what Lhopitals rule says is we can evaluate this limit by saying the derivative of the top, which is going to be 2x plus 1, over the derivative of the bottom, which is 2x plus 2. And after we use Lhopitals rule, and also sometimes when people use Lhopitals rule, instead of just saying is equal, they put a little h above the equal like that to indicate that we're using Lhopitals rule. So now if we plug the 3 in, we get up top, this would be 6 plus 1 is 7. And on the bottom, we've got 6 plus 2 is 8. So this limit is 7/8. And we found that using Lhopitals rule. Now, we could go back and do this the old way by taking the top and bottom and factoring them. Now, 3 made the top and bottom both go to 0. So that means we can factor both of these to have x minus 3 in them. The top, the other term, or other factor is going to be x plus 4, and on the bottom it's going to be x plus 5. And if we cancel these guys, we're left with 3 plus 4 on top and 3 plus 5 on bottom. So that's Lhopitals rule. Or rather, this up here was done using Lhopitals rule. I wanted to do one example at least where we did it both ways to see that it gives us what we would normally expect. The thing about Lhopitals rule is it works in some other situations. Like this right here, if you plug in the 0 for this one, you got limit as x goes to 0 of cosine x minus 1 over x. If you do this, the bottom is obviously 0. The top, if we plug in the 0, you get cosine of 0, which is 1. So that's 1 minus 1 is 0. So that tells us we can use Lhopitals rule. So let's see, derivative, we still need the limit. Derivative of the top is going to be minus sine x. Derivative of the bottom is 1. And now if we plug in the 0, you get minus sine 0 over 1. Of course, sine 0 is 0, so we get this. All right, let's play with this one on Desmos for a second. On this one, if I plug in, or if I graph y equals cosine x minus 1 over x, we get this graph. And if I zoom in here, you can see that it looks like it goes straight through 0 there. But if I zoom in and actually get this on the point, see 0, 0, 0 there. Well, when x is 0, the function's undefined. But we can look at it and tell that basically that the y-coordinate of this open circle on the function is 0. So Lhopitals rule gives us this limit. Let's look at this next example. X goes to 0 of sine 6x over x cubed plus 2x. If you plug the 0 in there, then you get you're going to get 0 over 0. So let's use Lhopitals rule. X goes to 0. Up top, you take the derivative of sine 6x, you get 6 cosine 6x. On the bottom, we get 3x squared plus 2. All right, so after Lhopitals rule, we need to plug the 0 in again. You plug the 0 in, you get 6 times cosine of 0 over 3 times 0 squared plus 2. So the top is 6 times 1, and the bottom is just 2. So our answer is 3. And we could graph this on Desmos if we wanted and see that this is the point. But let's don't do that, though. All right, let's look at this one now. The limit is x goes to infinity of these two things. Now, this one, we've already seen how to do this problem. We've got a polynomial over a polynomial, and both of them are degree 2. And so from looking at the leading terms here, we know the answer is going to be 3/4. But let's say we didn't know that. We can get the same answer using Lhopitals rule, because this is an infinity over infinity type. All right, I have a cat on my keyboard, or on my iPad. All right, so this is infinity over infinity. So let's use Lhopitals rule. So when I do that, I've still got my limit as x goes to infinity. And let's see, up top, what do we have? It's going to be 6x plus 1. And on the bottom, we've got 8x plus 9. Okay, so we're kind of in the same boat here. We can look at it now and say, well, we could look at it and say, okay, then the answer is going to be 6 over 8. But let's use Lhopitals rule again, because it's still an infinity over infinity type. When x goes to infinity, the top and bottom both can go to infinity. So if we use Lhopitals rule one more time, up top you've just got 6, and on the bottom the derivative is 8. So our answer here is 6 over 8, or 3/4.